In this video, you will learn how to find the concentration of reactants and products at equilibrium in a closed reversible system. Examine this question carefully. You are presented with a reversible reaction, and you are tasked to find the value of its equilibrium constant in terms of concentrations. Now, let's look at the remaining information. You are given the amount of reactant that the reaction begins with before dynamic equilibrium is achieved. However, you are not given the equilibrium concentrations of the reactants and products. The purpose of titrating the mixture with sodium thiosulfate is to determine the amount of iodine present at equilibrium. During the titration, iodine is reduced to iodide, and therefore the concentration of iodine at equilibrium will drop. A system at equilibrium will respond to this change by opposing this reduction through increasing the rate of the forward reaction so as to produce more iodine. So, if too much time is taken, the amount of iodine reacted with the thiosulfate would be more than the amount originally present at equilibrium. Let us continue on to find Kc. To do that, we must first obtain the equilibrium concentrations of the reactants and products. Begin by constructing an ice table. Write down the balanced chemical equation for the reversible reaction. Draw 3 horizontal rows below the equation. Label the first row initial amount, the second change in amount, and the last equilibrium amount. All of them are measured in units of moles. Divide the rows into as many columns as there are reactants and products. For example, in case you're wondering why this is called an ice table, take a closer look at the first letter of each row. We were told that the reaction started off with 0.0250 moles of hydrogen iodide. Hence, we fill in this value under hydrogen iodide and along the first row. Since there were no products present at the start of the reaction, we fill in 0 under hydrogen and iodine and along the first row. By titrating the reaction mixture at equilibrium with thiosulfate, we can determine the amount of iodine present at equilibrium. We fill in the obtained value of 0.00140 mole under iodine and along the third row. From the stoichiometry of the reaction, the same amount of hydrogen must also be produced as well. We also fill in 0.00140 moles under hydrogen in the third row. Since we began with 0 moles of both hydrogen and iodine, there is an increase of 0.0014 moles, which we reflect as positive 0.0014 mole in the second row of the ice table under both hydrogen and iodine. From the stoichiometry of the reaction, 2 moles of hydrogen iodide would be used up for every 1 mole of hydrogen and iodine formed. Hence, the decrease in number of moles of hydrogen iodide would be twice that of the increase for hydrogen or iodine. The amount of hydrogen iodide present at equilibrium is therefore what remains after deducting the amount used from the beginning amount. And our table is completed. To find Kc, we require the concentration of the reactants and products in moles per dm cube. Since the volume is not given, we let the volume be V and we obtain the equilibrium concentrations. After deriving the expression for Kc, substitute in the respective concentrations of reactants and products at equilibrium. In this case, the unknown V cancel each other out and we finally arrive at the value of Kc. Don't forget the units. Now you're going to find the value of Kc for this reaction. Examine the state symbols in the chemical equation carefully. You'll find that they are all liquids. If we were to exclude all of them from the Kc expression, there would be nothing left to write. However, in this case, they are not acting as solvents, but as reactants and products. Therefore, all of them must be included in the Kc expression. Pause the video and resume when you are done. Let's check your answer. Did you construct the ice table correctly? Since water is a product in this reaction, there are altogether 4 columns. You were given the initial number of moles for both the reactants, ethanoic acid and ethanol. These belong in the first row of the ice table. And since both the products, ethyl ethanoate, which is an ester, and water are not present at the start of the reaction, their initial number of moles is 0. The amount of ethyl ethanoate at equilibrium is 0.079 mole. This was given in the question. And from the stoichiometry of the reaction, the amount of water formed is also 0.079 moles. These values belong in the third row of the ice table. We are thus able to calculate the change in the amount of product formed, which is an increase of plus 0.079 mole. From the stoichiometry of the reaction, there is a decrease in the amount of reactant by minus 0.079 mole. And the second row is completely filled up. The amounts of reactants remaining at equilibrium are therefore 0.021 moles and 0.071 moles for ethanoic acid and ethanol respectively. As the volume is not given, we make use of V in writing down the concentrations of the reactants and products at equilibrium. As mentioned earlier, in this reaction, all the substances are not acting as solvents. Hence, the equilibrium constant expression is the concentration of ethyl ethanoate multiplied by the concentration of water divided by the concentration of ethanoic acid multiplied by the concentration of ethanol. Each concentration is raised to the power of 1, which is the stoichiometric coefficient in the balanced chemical equation. Substitute in the equilibrium concentrations, V will cancel off, and we obtain Kc to be 4.19. And there are no units. Continuing with the question, you are asked to find the amount of the product ethyl ethanoate at equilibrium when the starting amount of reactants are changed. To do this, it is important that the reaction occurs at the same temperature as when we calculated Kc previously. The method used will also be slightly different. We will therefore treat this part of the question as an example. Construct the ice table and fill in the initial amount of reactants and products. This is where it starts to get interesting. In our previous example and exercise, we had the amount of one of the products at equilibrium, which led us to progressively fill in the empty positions of the ice table. This time, we have none. To proceed, we therefore let the amount of one of the products at equilibrium, say ethyl ethanoate, be equal to X moles. From the stoichiometry of the reaction, the amount of the other product at equilibrium, water, is also X moles. We fill in these values along the third row of the ice table. The change in amount for both products is then plus X moles. And from the stoichiometry of the reaction, the initial amounts of reactants would have changed by minus X moles. And the equilibrium amount of both ethanoic acid and ethanol are written as 0.2 minus X moles. We obtain the concentration of the reactants and products at equilibrium like before. Write the equilibrium constant expression. Substitute. Since a particular value of Kc is constant for a given temperature, and we are using the same temperature as before, the value of Kc is 4.19. We further simplify the right-hand side of the equation. Proceed to solve for the value of x. If we expand, we would arrive at a quadratic equation, which you could solve by using your scientific calculator or by the formula method. Fortunately, we could take the square root on both sides of the equation and obtain two possible values for x. We reject 0.391. 0.2 moles of reactants can at most only produce 0.2 moles of ethyl ethanoate, since the stoichiometry of the reaction is 1:1. Hence, the value of x to be used is 0.134, and this is the number of moles of ethyl ethanoate produced at equilibrium. In this final example, we look at an entirely gaseous system. The initial amounts of reactants are given, and so is the value of Kp. But the last statement demands the most attention. Construct an ice table and fill in the initial amounts of reactants and products. The question says to obtain 20% conversion of sulfur dioxide. 20% of the initial amount of sulfur dioxide is 0.4 moles. This means 0.4 moles must be used up at equilibrium, and that there must be a change of minus 0.4 moles. The amount of sulfur dioxide at equilibrium is therefore 1.6 moles. From the stoichiometry of the reaction, we see that the amount of oxygen used is half that the amount of sulfur dioxide, while the amount of sulfur trioxide produced is the same as the amount of sulfur dioxide used. And we obtain the equilibrium amounts of oxygen and sulfur trioxide. As the value of Kp is given, we will need the partial pressures of the reactants and products at equilibrium. Recall that the partial pressure of a gas may be obtained by multiplying its mole fraction with the total pressure. For each mole fraction, substitute in the respective number of moles of that gas over the total number of moles of gas in the system. For example, the total number of moles of gas in this system is 1.6 plus 1.8 plus 0.4, which is equal to 3.8 moles. Hence, the mole fraction of sulfur dioxide is 1.6 over 3.8. The total pressure is the unknown that we want to find. Write the Kp expression. Substitute in the partial pressures of the respective reactants and products. We use the given value of Kp as 0.13 atmospheres. We solve for the value of Pt, or total pressure, and its value is 1.02. Hence, the total pressure required is 1.02 atmosphere. You should now have the necessary skills and understand the different techniques to perform calculations that involve the equilibrium constant.